Thank you very much to everybody for be here. The next speaker is Saul Vélez. He will talk us about spintronics and nano devices lab. Thank you very much.
Yeah, thanks for coming. I know we are starting a little bit late, so half an hour waiting here, so but it's fine. I mean, you could have told me, also I could have had a bit longer lunch, but it's okay. So yeah, take a seat and we'll start. So I want to thank the organizers for making this happen today and for inviting me to present my experience since I arrived here at UAM. So the first thing, they told me that I should share a little bit, so how things have been for me, and of course present a little bit of what we are doing, right? So the first thing is, okay, so what we do is we try to make a spin-driven effects. So we try to explore spin-driven effects in magnetic thin film magnetic nanostructures. So things that we explore, for instance, are how we can transport spin information through magnetic insulators via the excitation of spin waves that are commonly known as magnons, or how we can manipulate domain walls or let's say magnetic textures even in magnetic oxides. But I will explain a little bit more. Before that, so how things were for me when they told me, like in 2020 call, that I was getting the position to start a new lab. Right? What do you think as a student, maybe what a professor is doing? So when you get the position as PI is like, okay, so the person, I mean, the PI is not gonna do anything. And it's like just, like a student trying to get students getting things done, right? But as experimentalists at least, so probably this doesn't work for theoreticians. Maybe theoreticians work in a different manner, but I can tell you from my experience as experimentalist that things are a bit like more difficult, right? So basically, you got already here, so you are not, let's say, in Saul, in central Madrid, so you are somewhere already, but you still have to climb all these things, so you have a lot to do. And yeah, basically you have to push things to move forward. But then it comes the Spanish system and UAM that is just I've also to suffer from the Spanish system itself. So it doesn't. It's not that that the UAM can do by themselves what they want, right? So the bureaucracy is tasked, and so who has problems with getting this contrato menores accepted, right? So months and months, delaying for things that buy just, 1K. You want a new computer, there's a new camera, is 1K, and you have to wait half a year. So it's kind of pain, right? And then you think, oh, we have great facilities, we have second base, maybe we can order something there. And okay, you order today, you get it next year. So plan in advance, right? But you have to start your lab, so you need things ready now. So that is a bit tricky, but I can't complain so many things, but one of the very first things that I had in my lab was like, okay, so I have everything, or supposed to have a lab there, but I did not have internet. And Kao told me that, okay, so we don't have new switches, we have switches, we don't have, everything is busy, we cannot give you internet. And ticket closed, really. So no solution, and then I had to find myself, Eduardo, I know, I was coming to you, like, okay, do you have any switch there that you don't need? And then I was taking one port and making a local Wi-Fi and try to live somehow, right? And then say, okay, let's hire some people. But then comes the negotiation labor law, and again, you cannot hire anyone. So where is Priya? Yeah, if you have been waiting for 1 year or something like that to come here because simply everything was paralyzed for half a year or something. And then, because we were almost about the point that your contract was there, we had to start from scratch because anything done before was not worth anything. So, okay, so let's start. But then, okay, so that's what we had 2 years ago, an empty lab. Now we have something that looks like a lab, right? So we got something. So this year, especially, that now that we have Haripriya and Pranab around, so we did a lot of work. So they can do some experiments that try to set things around. So I can show you a little bit what we are doing. So we have magnetotransport set up, so we can basically inject with an AC/DC current source. We can inject current to our device that is sitting here. So we have an electromagnet. We can apply 2 Tesla, and this will record the voltage as we apply an AC current. So we can be take the measurements in continuous mode, and then we do process analysis by computer. So that's how it looks a bit closer the setup. So here is sitting the sample. So that's what you see. So this is the sample. So it's very small, and even smaller. Inside this, you have these very tiny things. That's what we contact, and we use this wire wonder that we have in the third floor. So Christina, thanks for making this as a service for everybody. So it's very helpful for us. We have a bunch of samples that, because in the end, what we want to do is a lot of devices in the same chip, and then because you are changing here parameters, you can measure whatever you are aiming for, right? And here we have a motor stage. We can rotate the sample and so on, and take these AC transport measurements. How is a measurement looking like? So what are we doing actually? So that's our whole bar, for instance. Here we run an AC current, and we try to measure, voltage here, transversal or longitudinal. And now what we have here in particular is we typically use a material with large spin orbit coupling. And these materials, what happens is that when you run a current, you get a deflection of these electrons that depends on the spin. They scatter to opposite surfaces. And this means that you have now a transverse spin current, you have spin accumulation, and now if you put this guy next to a ferromagnet, so what's happening is that you can drive some effects to the system. For instance, you absorb these spins, and these spins exert a torque, because spin have angular momentum, you exert angular momentum, you transfer this angular momentum to the magnetization, and then you exert a torque. And there are 2 types of torques, and then you can make and now here is like a side view, right? So we have here your heavy metal, that's a platinum layer, that's our ferromagnet. Typically work with garnet, so that's what I'm gonna show you today, a couple of measurements. And you run a current now, and these spins that you generate, they interact with the magnetization, then you make these guys to oscillate out of plane, that's it's called anti-damping like torque, and they can also oscillate in plane, that's called field like torque. And that you see when you see this in harmonic transport measurements, basically these oscillations what you pick up as second harmonic. So that's the derivative of so the oscillations that you are getting in your magnetization is what gives you an additional non-linear electron resistance. That's what you pick up in the second harmonic. And in the first harmonic, you pick up whatever standard measurement you will do with a DC measurement. Essentially, that's what you are more used to. So that's how, for instance, a whole measurement look like. So that's what's called planar hole. Maybe you're familiar with this, maybe you're not, but that's how it looks like. So these tracks where the magnetization is pointing to, and that's simply assigned to angular dependence. But then you have these torques that I'm talking about here. So these have these particular angular dependences. These are the anti-damping like torque. So here we are rotating the magnetization in the plane, right? So that's what you are getting. And the amplitude of this effect depends on interface quality, how much spin you are generating, etc., how much current you are applying, etc. And then on top of that, you will also have other effects like thermoelectric effects. And these also appear in the second harmonic. So essentially, if you just stay with the first harmonic, what typically people do is you do this. If you do higher harmonics, you do this, and more things also. And that's what I'm trying to show you today with Haripriya. That's what we are doing now. So we are working with platinum on top of yttrium iron garnet. And now when you apply a very large magnetic field to control where the magnetization is going, so if you see that you have used AC current applying, and these oscillations, you are damping them, right? So you are getting small damping. So then you see this damping torque. So for the large field, so 400 millitesla, you only see the thermoelectric effect. That's spin-civic effect. I'm not going to explain everything how this works now, so I'm going to show you a little bit later. But in the end, it's like a thermal gradient out of plane, and depending on the direction of the spin, you are pumping spins to the platinum, and that's what leads you to this non-linear magnetic effect. And then on top you have this field-like torque that the measures when you have small fields, and that's very strongly dependent on the field, and particularly is 1/b. Okay. And now, if you take this yttrium garnet instead of a thick one, you take a very small one. We see the effects that we saw for the thin one and for the thick one, but we see an additional magnetoresistance effects, and that's something related to magnon creation annihilation effects. So maybe Akash, sometimes maybe can help us a little bit understanding this and the thickness dependence, because it's not just 1/thickness, so not just magnetic volume, it's a little bit more than that. And that's, we are still preparing and trying to make fits. So what we interpret this is that we are compensating the damping in the system because we are pumping spins in the system. And basically we have this additional angular dependence that leads to a new magnetoresistance effect. That's a new magnetoresistance effect that relates to this spin pleated scattering because of the creation of magnons. Let me connect to what magnons is. So what magnons are basically. So now again, so we have this heavy metal, we run a current, we generate these transverse spin currents. Now you think that these spins maybe can be absorbed by the magnetization, then pump here basically one magnon, so absorb one quantum of angular momentum from the spins, and then you have a spin flip scattering here, or magnon can be absorbed by the spins at the interface. So you can get creation annihilation of these magnons. And you can do also this by reversing the direction of the current. That's what we continuously are doing in magnetic measurement. But now, if you place this guy, so this electrode on top of this magnetic insulator, now you run a current, and because of these magnons, they can also propagate, right? So they are propagating because you have interaction here, so you can generate these magnons, and then now you place another electrode, and even though this is not electrically conducting, you can transport spin information through this magnetic insulator force of magnets. And then you can pick it up with a reciprocal process. On side reciprocity, you will get exactly the opposite process. You will convert these magnons to charge to a spin current, and this spin current to charge current. What you're picking up here is a voltage. Let me show you. So, but we have this as a spin, but you have also these thermal gradients that we were talking about before. And so you are generating also a thermal gradient, this interface, because you're running current, so you generate this thermal gradient. So now you forget about the spins at the ejector, and you get this thermal gradient. So this also drive magnons, because a thermal gradient in a magnetic material just leaves a non-equilibrium profile of magnons. So this will be diffusing away and be also collected at the detector, the investment Hall effect. So now via these harmonic measurements, so we can decouple the spin driven, which will be in the first harmonic, and the thermally driven, which will be the second harmonic. And that's how a measurement looks like for the spin driven one. So it looks like a sine square, and that's just because of the symmetry of the spin injection at the injector and the spin detection at the detector. And in the case of the thermally driven ones, so we have a little bit more than just picking up magnons, because you can also have thermoelectric effects. So you have magnons that are driven by dotted plane thermal gradient at the injector, but you can also have thermoelectric effects, because in the end you will also have thermal gradients at your detector, and these you need to also account for this. And these ones, for instance, similar to what we saw before with damping. So we also see that if we apply a very large magnetic field, we are also damping these magnons, and we don't let them propagate that much. So we see that this amplitude of the signal is decreasing substantially as you increase the magnetic field or increase the distance also. By measuring this amplitude as a function of distance, you can extract how is this guys are diffusing, they are diffusing exponentially, etc. But I'm not gonna enter in more details in that. So now, what else we can do? So we do also magnetoptics. And this is or maybe we need still to cover this guy, because we cannot work this in open light, because otherwise we have a lot of let's say background light coming to our camera. And we work with so here I'm just pointing the most important ingredients that we have in this tabletop microscope. So we have a LED source, And we have here a series of lenses and so on to collect the beam and make like a parallel beam. But then you have a polarizer. See, this one of the most important parts. So the light comes non-polarized, and you polarize a certain angle, and then this light you focus on your sample that is here. Now what's happening is that light comes with certain polarization, scatters with the magnetization. You have certain shift, and now what you try to pick up this shift is with the camera. And what you do is to phase analyze at this 90 degrees, and then you are sensitive to very small changes in this rotation angle. That's called Kerr effect. That's for polar configuration. And that's what we are trying to do. So measure these tiny changes when we are reversing the magnetization in the sample that is autoplane magnetized. When certain domain is reversing, so we have a change in the intensity. Now that's how the guy looks like when you shine light. So this still in optimization, but that was the very first image. Was not in the computer, was on the wall when we did not have the camera set there, and we could see already the device was there. And then later, with a little bit more work, we could get these magnetic contrast images. Here you can see up and down domains, and that's with the ferrimagnetic layer. So ferrimagnetics have much less magnetic moment than ferromagnets. So that means that was already a success that we could see a ferrimagnet, and this was a few nanometers thick. So we could see something. Now we still have a lot of to optimize to start with covering it. So where is Chema? Chema, isn't it here? Okay, so I need some help from here. So now what science we can do with this? So what we do is now we have this material with perpendicular magnetic anisotropy. We run some current through a platinum layer that is on top or on the bottom, whatever stack we are doing, doesn't matter. So this is how, for instance, this device look like. So we have two Limeron magnets, so that's for magnetic system for choice. So we have autoplane magnetization for this guy, and we run current through the platinum stripe. So that's part of this device, right? So we run current, and then we can deterministically, so controllably, we displace this domain wall. And that happens because we have an interaction of these spin currents with the magnetic texture we have. And we have to have a particular magnetic texture because if we don't have what's called Nell type domain wall, the coupling will not be correct. So it will be block type, will not be coupling, and so on. So the type of torques that you accept to the domain walls depends on where the polarization of the spin is pointing to and which type of domain wall you have. And the interesting thing here is what you have is that this platinum layer, that is the one that helps you to inject spins, brings the spin orbit coupling to the system. And that the spin orbit coupling is what helps you to stabilize this type of domain walls. So that system basically, or this stack, is helping itself to get these domain walls that you want to have to drive these domain walls. And then we went a little bit further and we could also stabilize skyrmions in the type of magnetic insulator layers. And you have to think that these are non-conducting magnetic layers, and we can drive them, and the velocities that you get, the figures of magnetic velocities that you get, are similar to the metallic ones. And the idea is that these materials could be, because they are epitaxial, have very low damping and so on, they could even have potential to surpass the current metallic technology. And then the very last thing I'm going to show in terms of results. So things that we are working now also, that's more on Pranab side. Still, we did not do measurements with this because we don't have optimization zone, but we had some previous measurements where I was at ETH. And we want to work with ferroelectric materials. The ferroelectric materials are, we are maybe more familiar with magnetic systems, but ferroelectric is not that much. So we have spontaneous electric polarization in the material. So these guys retain this electric polarization. You apply electric field, so you can reverse the polarization, and this polarization, electric polarization, can be up or down. And now what you think is what's happening at the Z interface. The Z interface, this field some local electric field. And this is equivalent to like shifting properties by electric fields. And it's known in literature that you apply a static electric field to a magnetic system and you change properties of the magnetic layer, like stabilization of chiral domain walls or Jackson spin conversion phenomenon, for instance, at the interface. And that's what we want to do. And the interesting thing here, because you to remove the electric field, you retain this polarization, then you are statically, let's say, you have non-volatile change in the properties of the system. What we see is that we are changing the velocity of the main walls, which is related to this interfacial interaction that is what is called to the stabilization of the chiral domain wall. So you have different interaction that is called Jelinek-Morier interaction that you are tuning by the ferroelectric polarization. That's the field realization of this type of experiments. And work in progress, so in finishing. So basically now we are also setting up Prophet station. We're working on that. So we have everything. We don't have the table yet. Things are, busy in the second section here and there. And hopefully we'll get the tables on at some point with table, etc. And we can get this thing done. And now we have also a chamber that is in the process of getting it. So we already ordered this. Contrato menor needs to be accepted also. And this will allow us to go to low temperatures, and we will have possibility to have transport measurements at the same time that we have an optics window, and we can do both transport and magneto-optics down to 8 Kelvin. It's not like helium cooling, but this will improve a lot of our capabilities in the lab. And this is very compact, so we can put it in our electromagnet, and we can get easily with the gaps that you will have in the electromagnet more than 1 Tesla. And with this goes to the most important slide of this presentation, with especially all the people that contributed to the work and contributed to getting me here. FJ at that time was supporting me a lot, Ruben, Almudena, Beatriz, with all these, contratos menores, all the administrative things, etc. My previous students, my current students. So we have really a lot of things to do in the future. And yeah, Akash, we also work together a lot. And my previous supervisors that brought me here and the funding, because I was lucky, I brought the talento and also the national project, etc. Thanks you all for your attention.
It's time for questions.
It's a technical question, thank you very much. For the experiments, where do you get the Jelinek-Morier interaction in thin film?
So in that sample is essentially from the platinum on top, but both the metal oxide and oxide-oxide interfaces contribute. In the case of thulium iron garnet solely, we have also from the interface with the substrate. But in that one with the skirmions, the platinum on top is the one that was dominating, and we had right-handed nail.
And is this stable with temperature?
We did not have before capabilities to experiment at different temperatures, but now maybe soon we can do also some experiments. And actually we want to do in these samples like spontaneous skirmion diffusion. That could be a nice experiment to implement. You increase a little bit the temperature, we expect large mobility of these skirmions, and spontaneously they should be moving around doing some Brownian motion. That's very easy experiment to implement if you have capabilities to increase a little bit the temperature, and that's what we can do now with this new system.
More questions? I have a curiosity, okay? It's a very technical curiosity, and it is about the devices. How do you fabricate this arrangement of platinum electrodes? Do you fabricate them here by yourself?
These ones, no, but we have other samples that we are fabricating. So I skipped some parts that on fabrication new samples that we are working with. We grow in India. So we have a collaboration, the national project, we have a consortium, and we are growing there the samples, and we use their clean room. Hopefully in the future we can also use the EVL and the laser writer, etc. that we will have at IFIMAC. Okay. But for now, that's what we do. So we grow the films first, and then we do etching.
Okay, thank you very much, Saul. I think let's move to the
el puntero de sí, porque
Okay. Our next speaker is Paloma Arroyo with Oro, and she will tell us about her research at IFIMAC. Thank you very much.
Thanks. Thanks for the introduction, and thanks also to the organizers of the IFIMAC Day for organizing the event and for having me here. So yes, I want to tell you a little bit about what I am doing here, but first let me. So first let me tell you how I got here. So many of you already knew me before I got here because I did my PhD thesis in the condensed matter theory department with FJ. I defended my thesis in 2013, so I did my thesis in IFIMAC. This is a picture from those days. You may recognize some faces, FJ, Johannes, Esteban, Jorge. Antonio and Diego are not in this picture because they had already left to do their postdocs. But Diego was kind enough to provide me also with some other pictures of the many social events that we used to enjoy back in those days. So after finishing my PhD, I moved to Imperial College as a postdoc for a few years. And right after that, I moved to Lisbon, where I spent 3 years as a researcher. And I had the opportunity to experience how to try to set up your own group without the appropriate support for it. So then when in 2022, I learned that I won the Ramon y Cajal and that I would be coming back to IFIMAC, I was really happy about this news. And I was really sure that I would be coming here to a very welcoming community and a very supportive environment. So for this, I just want to thank everyone at IFIMAC. Okay, so let's now talk a little bit about science. With this talk, I would like to just give you a brief overview of the physics that I'm studying. Okay, so and I hope I will not take very long. So just as general background, I did my PhD in the area of nanophotonics. Many of you know about this field. So the main motivation behind it is that nanophotonic structures allow us to confine light in the nanoscale at the nanometer scale, but even beyond the diffraction limit. So and this becomes very interesting when you think about light matter coupling and enhancing QED processes. You can do this, so QED processes that can be just vacuum processes of the electromagnetic field, but also interactions with quantum emitters or between quantum emitters. And this is something that is present or can be present even at room temperature and in the nanoscale. So this is a bit the motivation behind all my work. Now, after my PhD and while I was a postdoc at Imperial, I started to work on a related topic, but that was newer at the time. And it was the idea to think about modulating material properties in time. So thinking about time-varying media, time-varying medium properties. So the motivation behind this is that conventional nanophotonics, and by this I mean static, linear, and passive systems, are constrained by fundamental principles of energy conservation and reciprocity. And modulating properties in time allows to overcome these limitations. Okay, so for instance, it is easy to understand that modulating the optical properties of a material in time allows to break energy conservation. We are breaking the time reversal symmetry. Energy does not need to be conserved, and this allows one to obtain different frequencies and to obtain gain. Right? One can also think about breaking reciprocity by imagining modulations that couple space and time, and this allows to realize unidirectional light propagation of light, which is something that is usually very, very challenging to do. Okay, so here I have a simple sketch of a very simple physical process that may allow us to understand a little bit better what kind of processes we are thinking about when we have modulations in time. So here I have the case of wave scattering at the spatial interface. So this is the typical Fresnel problem that we all know conserves the frequency and interchanges momentum between the incident, reflected, and transmitted waves, right? So the dual to this is a temporal interface where the refractive index of a medium is changed abruptly in time. So in this case, what is conserved is momentum. So if we look at this band diagram, this now is represented as a vertical transition, and frequency is what is changing. So now, if we look at our incident wave, what we have once the medium has abruptly switched the refractive index is a temporally refracted wave, which is just a frequency shift. It's a wave that propagates in the same direction as the original one, but we also have a temporally reflected wave, which, because of causality, it cannot actually propagate back in time, so it propagates back in space. And this wave appears here as a negative frequency wave. It's nothing else than a phase conjugated wave. Okay, so we see very clearly, and in an easy example, that time reversal symmetry breaking allows to break energy conservation. So now, what are the physical platforms? So I'm a theorist, as you know, but what are the physical platforms that are behind this field and the interest in this time-varying media? So at the very beginning, most of the physical platforms were mainly reduced to low-frequency metamaterials, transmission lines, but this essentially because it is not very difficult to tune the properties of a medium if you have access to electronic means. So if electronics is fast enough compared to the frequency of your waves, right? And this allowed people to do things like measuring this time reflection of electromagnetic waves, which surprisingly had not been measured before. The challenge here is that the reflection coefficient is proportional to the change in impedance, so you actually need a very strong and abrupt change in impedance to be able to measure that. And then this has only been measured at low frequencies. But nanophotonics, coming back to the introduction, also comes to help here to bring the field to higher frequencies. So for instance, one can play with nanophotonic antennas, in this case some dielectric antennas with a nonlinearity, and the pumping of two lasers that are counter-propagating, and that generate a modulation that is coupled in space and time, so it is propagating as a traveling wave. So, and with this, they were able to observe non-reciprocal reflection, for instance. But even more interesting are some media that are usually called, referred to as epsilon near zero media. So this includes the transparent conducting oxides, which are semiconductors that have a plasma frequency in the near infrared range. And what this means is that when the real part of the permittivity crosses zero, the nonlinear effects are boosted by a very large magnitude. So, and by very large, I mean that materials at close to these frequencies can experience changes in the refractive index that are of the order of the refractive index itself. So this gives a promising platform to try this physics where the refractive index can change very abruptly and very strongly. And some experiments that have made use of this are, for instance, this one, where they showed frequency shifts through temporal refraction, so the frequency shift that I was mentioning before, of up to 10%, and then a double slit time diffraction. Okay, so let me now tell you a brief overview about my own work. So I'm a theorist, I enjoy simple things. So I will be taking the model of a periodic modulation, okay, and I will be telling you a bit about what we can find here. Okay, so we are all familiar with modulations in space. This is the kind of band diagram that we get when we have electrons in a solid or when we have a photonic crystal. Now imagine that our modulation of one of the parameters of the medium, say the permittivity or refractive index, is varied periodically in time. So now we have to replicate our band structure with using a reciprocal lattice vector that is vertical in this band diagram, right? So we have to do something like this. And from this, we see very directly that this temporal modulation can promote vertical transitions, right? As in the time reversed wave that I was speaking about. So something that these vertical transitions can be used for is to couple propagating photons into surface waves. So photons that are confined to a surface and that live beyond the light line, and that usually cannot scatter into free space because they, unless you corrugate your surface or you break the periodicity somehow in space to provide this momentum mismatch. So what we are doing here is we are providing the frequency mismatch by needed to go to scatter from free space into a surface mode by means of a periodic temporal modulation. Okay, so now we go back to our band diagram and we see that in these crossings we have in the crossing between a forward mode and a backward mode. And what happens here actually is that these two modes interact and they open up a band gap that is rather curious and that is very particular of wave equations. This is not something that would happen for a Schrödinger equation. And these band gaps are vertical gaps, they are gaps in K, and they host states of complex frequencies, so they host amplifying states. And this does not break causality because this is an open system. I am inputting energy to modulate the parameters. So these states are there and we have to live with them. And in fact, another way to see this is to think about parametric amplification. So this actually drawing this band diagram is a way to understand parametric amplification, which occurs at twice the frequency. When a system is modulated at twice the resonance frequency that would be here. Okay, so let's now think what would happen if our modulation was in space and time in a traveling wave form, as in the experiment that I was showing earlier. Well, now we have to replicate our bands in a diagonal way, but we have to be careful if our if this vector here, if the reciprocal lattice vector, has a lower or a larger slope than the velocity of light or the velocity of wave in the background medium. And what we obtain is that because of this tilting, we obtain asymmetric band gaps that are very interesting for non-reciprocity. So for instance, if you are at this energy, you can have a mode that propagates in the backward direction, but sorry, I'm not pointing correctly, no, but you see the point, that you can have a forbidden propagation in the forward direction while having a mode in the backward direction, right? And then depending on this ratio between omega and G, you can get either the typical frequency band gaps, or you can also inherit these temporal-like band gaps. Okay, so something that we were wondering when we started working with these systems was the link between this kind of modulations that are actually represent a synthetic motion, right? They don't represent any physical motion of anything, it's just a phased motion. So we were wondering about the link between physical motion and synthetic motion. And for this reason, we were interested in deriving an effective medium description of this kind of space-time modulated media. So by effective medium, I mean that we were interested in looking at the band diagram far away from the band gaps at low frequencies and low momentum. Okay, so in order to understand this, we performed a transformation to a moving frame, so to a frame that moves with the modulation, where we can get rid of all the temporal dependence of our constitutive parameters that we don't know how to handle, and obtain effective permittivity and permeability tensors, and then move back to the frame to the laboratory frame, right? And the set of constitutive parameters that we obtain is something like this. And from this, we can immediately conclude something, which is that any synthetic motion that preferences one direction maps to a uniaxial effective medium. So these epsilon and mu are now constants, they no longer depend on time, but they have developed an anisotropic character. And furthermore, there is this bianisotropic coupling term that has arisen and that couples the electric and the magnetic field. And, and this is something that arose only due to the synthetic motion and is very linked or it reminds to the kind of constitutive relations that one has with moving media, actually. So media that actually move. So let's see what is the effect that these modulations have in the waves. We can do that by looking at the effective wave velocity that we can extract from the effective parameters that I just discussed. And what we find is that because this bianisotropic coupling changes sign between the modulation of the medium and phase modulation between permittivity and permeability, it changes sign, so we can get all kind of non-reciprocal behaviors. So we see that the light is really slowed down or speed up when it travels, when it co-propagates with the modulation, but it is barely affected when it is counter-propagated with the modulation. So this can actually be linked to what happens with light in a moving medium, as was revealed by the FITSO experiment, who was trying to show to prove the Fresnel-Eder-Drag hypothesis in the early days of relativity. And well, if you know about this, at the end of the day, this was explained by the velocity addition formula for special relativity and not by Fresnel argument. But the physical effect that FITSO measured is real. Light is dragged by a moving medium, and in our case, we are mimicking this with just a synthetic motion. This has not been shown experimentally in electromagnetic waves, but it has been shown in an analog system where they were studying charge diffusion. Okay, so I spoke about these band gaps in these two regimes, but what happens when the modulation speed is actually in between these two regimes? So when this reciprocal lattice vector is parallel to the light line, to the band, well, in this case, we have a very strong instability. All the forward modes fall over on the fundamental band, and we can no longer speak about block modes. And what the effect that this has is that in this system that has no gain, my only assumption is that I am modulating the permittivity. If I input a plane wave and I calculate the electric field profile at the outside of this, after the wave has propagated through a given length of this medium, I see that the field is increasing at a given point as a function of length. Okay, and even if there is no gain, I see this exponential amplification. And the explanation for this is that the wave is getting compressed in some points of the grating, and the physical process is that frequencies are summing up. Okay, this we suggested that can maybe be done by modulating graphene. Okay, and very quickly, a last example is that we can also get a different mechanism of amplification in this media when we consider a chiral modulation. So here we are imagining an isotropic medium where the principal axes of the permittivity and the permeability are being modulated in a traveling wave helix. Right? So what we find in this case is that as we increase the modulation speed, their interaction between different bands increases greatly until we encounter some exceptional points, after which the bands are imaginary, and at a critical point, these exceptional points come up to 0, and we have a completely broadband, pretty broken phase, which results in the selective amplification of one polarization of light when light travels to the medium. Okay, so just in conclusion, I have given you an overview about the kind of physics that one can expect in this kind of systems, and a couple of works about the outlook and the work in progress. So we have seen a few examples of what temporal modulations can do at the classical level, but temporal modulations can also be very interesting in when thinking about quantum electrodynamical effects. For instance, the dynamic Casimir effect is a well-known example. And combining these temporal modulations with nanophotonics, I have proposed that we can use time-varying nanophotonics to devise novel forms of control of QED processes. And this is the topic of a grant that will be starting soon. So just to finish by acknowledging my students, Jaime and Alejandro, my collaborator, FJ, and Maria Blanco de Paz, a shared postdoc between IFIMAC and the IPC, and all my other collaborators in this work. And thanks for your attention.
Thank you very much. Questions?
Thank you, Paloma. Very nice. I remind me of something that we think with Francesca now about the collatons in moving collatons, and where you can have an analogy with under reflection, because this phase conjugate scattering, I think you can connect.
Okay, perhaps I did not think about this. Thanks. We can maybe discuss.
Another question?
Thank you, Paloma. The modulation that you're thinking on is just real refractive indexes. If you will consider also the imaginary part, then
Yes.
more fancy.
Yes, so in general, the results that I showed, well, in the Venn diagrams that I was showing, everything was real refractive index, no dispersion, no loss, and so on. Then in the calculations that I showed, in some of them, so for instance, when we use graphene, dispersion is actually included, loss is actually included in the material, but still the real part of the permittivity is what is playing a main role. But then for the work in progress, this is something that we are doing. And then the question is, how do you consider QED effect in a modulated media that is also frequency dispersive, that is also lossy? And this is what we're working on, and it's a big question. Thanks.
If there are any other questions?